So, hi everybody. First of all, I would like to thank the organizers for having me here. I'm Cristina Martinez-Lombilla, a new Astro 3D member this year and postdoc at the University of New South Wales, working with Sarah Brough. Today, I'm going to show you the first detection of intragroup light at redshift 0.2 in the deep data provided by the Subaru Hypersupreme camera. But what's the intragroup light? The IGL is the diffuse light that spreads across the center of galaxy groups, and it is concentrated around the brightest central galaxy, or BCG. This light is composed by stars that are unbound from their host galaxy due to interactions, so it is a fossil record of the interactions a system has undergone over time. And why is this IGL important? As I just said, the intragroup light is formed due to interactions between galaxies within groups, so it is a key parameter to map the mass assembly history in dense environments. And actually, when simulations of the BCG's growth consider that a percentage of the stars that are supposed to merge with the BCG, they will end up in the diffuse component, they reach a much better agreement with observations. However, this IGL is very faint and in fact is one of the most challenging features to detect. We are talking about reliable detections at Saffir brightness limit fainter than 26 magnitudes per second squared. And in consequence, there are very limited works with very limited samples. It has been basically detected in dense, strongly interacting groups, like compact groups, as these strong interactions are able to expel the diffuse material to large distances. And of course, this detection has been achieved in nearby systems. I'm always talking in detections of individual groups, not using any stacking procedures. So let's talk now about the data. We are particularly interested in the LSST, as this survey will provide the deepest optical image of the southern sky. It is going to be 10 years continuously observing. And in order to start being prepared for it, we are going to work with the data of the Subaru Hypersupreme CAM data release 2. And now you will see why. Current galaxy evolution studies are biased to the high Saffir brightness galaxies and structures. So in this plot is showing the limiting magnitude of the main surveys as a function of the observed wavelength. The upper region of the panel corresponds to the brighter regime, and it is covered by past and current surveys. These are labeled with solid lines. However, the fainter regime is still to be discovered. And here is where we find Euclid and the Vera Rubin Observatory, which is the one that will provide the LSST survey, as they aim to try to cover those faint areas, observing both in optical and infrared. And here we can also see why HEC is optimal for this work. HEC is this solid line here in green, and we can see that this camera reaches the deepest optical data of any current survey. So this together with other main reason that it is that the reduction pipeline is a custom version of the one of the LSST. So HCC and LSST share the same kind of data structure and outputs. So this is going to make our path easy towards the LSST too. So what we do is to use the HCC regions that are overlapping with the GAMA survey in order to take the information of the groups from their catalogs. And now I will show you the key steps in our methodology and the very first results for one of our groups. Here you have the reduced image of one of our galaxies, a group of galaxies, We have developed a method to detect and analyze the IGL in the most automatic way up to the date. It is fully Python-based, so it is very modular and flexible, easy to adapt to different surveys and to galaxy samples, which is great, especially in talking about low Saffir brightness features. And this method allows us to reach a software brightness limit more than 30 magnitudes per second square in the I band, which is great, and it is equivalent to the LSST 10-year depth. So after the regular deep image treatments, such as masking and careful sky correction and many others that I don't have time to get into the details here, we subtracted the very bright stars in the field because they can contribute to overestimate our IGL. So by doing the subtraction of the 3 brightest stars in the field, we get this result. To do that, we use a very extended custom-made HCC PSF, show it here. And this is because we need to get rid of the scattered light from the brightest stars in the field that are present up to very large distances. And as I just said, they are contaminating our IGL measurements. To do the subtraction, we scale the profile of the PSF to each of the brightest stars and then subtract that scale PSF model over the observed data. It is important to note that you still see here the core of the stars, but this is because we need to obtain a very good model of the outer parts. So we are not interested in the core of the star. We are interested in this component that it is contaminating or potentially contaminating our IGL. Over this image, we then perform a 2D model of the galaxies in the group, accounting for the intragroup light and also convolving these models with the extended PSF I just showed you. By subtracting the models of the group galaxies here, we get this beautiful image of our IGL. We can see how the IGL has been carefully preserved around the core galaxies, and the image is even showing a tail towards the upper right region, and this is because there is a galaxy of this group in that area. To generate our model, we use the astronomical software INFIT. We perform a 2D model convolved with the extended PSF for each of the galaxies, and we also add an extra exponential function to mimic the IGL around it. We then subtract the galaxies from the image, as I explained before. So it is always very difficult to be sure how to separate galaxy components overlapping one each other, and especially when one of them is so faint as in this case with intragroup light. And this is the reason why we model all the components at the same time in order to have consistent results between all the group members. Zooming in, it is clear how the IGL is spread around the group center and that the residuals from the galaxies are minimal. So now the next step is to analyze this IGL, and I'm going to show you just a very brief analysis we have already done. We extracted a radio sapphire brightness profile from the center of the group with reliable detection of the IGL up to 140 kiloparsecs. The profile shows that the IGL can be detected below 26 magnitudes per second square, as expected. And actually, this IGL detection is reliable down to our sapphire brightness limit, which is very, very good sign. So our results are in good agreement with those on the right from the work by Ragus and collaborators in 2021. They obtained the most extended estimation of IGL in a nearby group, reaching up to 160 kiloparsecs from the center of the group. In our case, we get the first intragroup detection at redshift 0.2 and the second most extended one. And we are currently working on further analysis of the data in order to fully understand these findings. So finally, as a summary, we can say that we have developed a method to measure IGL within gamma groups using HCC data. And indeed, we have detected it. It is great. The next steps now are to give the finishing touches in terms of testing and improving the method, and then, of course, analyze those IGL detections and do the actual science. And this will include to measure the fraction of IGL in the group versus the mass and redshift, which will provide key information on the formation processes and timescale of the mass assembly, and to track the colors for provide constraints on the progenitors of the system. We would like to repeat this for a statistically significant sample of groups and, of course, extrapolate those results for the LST depth to see what we would get. So this is all on my side, and please keep a look on the upcoming paper with all these results. Thank you so much.
Thank you, Cristina. That was really interesting stuff.
Thank you.
I have a question just while we wait on the Slack. So you've talked about the intragroup light, which is built through interactions, but this exists at like all mass scales. So you have stellar halos and the ICL as well. Is there any unique difficulties to the group mass scale that makes it particularly challenging, or is this a similar problem to like defining intracluster light observationally?
Yeah, I mean, intrinsically, it's similar, but the difference is the mass of the system. So the more mass in the system, the most diffuse component is generated, because there have been more interactions, or more powerful interactions, let's say. So it is. The amount of intracluster light is always going to be much higher than the amount of intragroup light, so that makes it a bit easier to detect in terms of stellar density, which is actually what we need to have light and to being able to detect it. So the problem of the groups is that we have less members and less mass, so less interactions.
Sure. And do you see different types of profiles between like your results of the IGL versus the ICL? Or?
Not for the moment. We haven't found anything different. Actually, the profile is quite smooth. At the very beginning, it's a bit more exponential, let's say, because probably there is still some contribution from the halo part of the galaxies that is not always perfectly subtracted and separated from the IGL. And then we have a very smooth distribution, which is what we expect. Basically the same down with IGL.
Okay, great. Thank you for that.